Hey everyone, this is Mr. Beckstrom, and today we're going to take a look at this problem here where we're given a polynomial function. It's already factored for us, and we want to answer some questions about the roots and the multiplicity and its end behavior and whether it crosses. So let's kind of go through each one. So first of all, we're dealing with the polynomial function, which is f of x is equal to 3 times x minus 3 times x plus 9 quantity squared. So the first one says list each real zero and its multiplicity. So remember, when they say real zero, this is actually the x values where it either touches or crosses the x-axis. So the imaginary zeros are ones that do not touch the x-axis. So it's nice that it's already in factored form for us. So we can just set each one of these factors equal to 0. So if we set x minus 3 equal to 0, just add 3 to both sides, and we get x is equal to 3. And it also says its multiplicity. Well, this factor that we got the 3 from only appears once. Since there's no exponent, we assume an exponent of 1, so that one has a multiplicity of 1. The next one here, where we have x plus 9 is equal to 0, is going to give us that root when we subtract 9 from both sides of x is equal to negative 9. Now, the factor that corresponds with negative 9, which is x plus 9, is squared. So that has a multiplicity of 2. What's also useful to us is that the first one has an odd multiplicity since it's 1, and the second one here has an even multiplicity since it's raised to an even number. Which is going to lead us right to the next question. It says determine whether the graph crosses or touches the x-axis at each x-intercept. So we look at that by looking at whether the multiplicity is odd or even. So for the x equals 3, where it touches here, it's actually going to cross through the x-axis since the multiplicity is odd. So here we're going to cross through the x-axis. And here, since the multiplicity is even, we are just going to touch it and go back the other direction. So we're going to touch it, but we're not going to cross through. All right. C, determine the maximum number of turning points on the graph. So turning points are going to be where you have your local mins and your local maxes. This is kind of where it's maybe increasing and goes to decreasing, or it's decreasing and it changes to increasing. And we can find that by looking at the degree of the polynomial and then just subtracting 1. So the degree of the polynomial is the highest degree that we're going to get. Now we could multiply this whole thing out, which is going to take us a little time, because first we have to FOIL this x plus 9 squared, and then multiply that by the x minus 3, which is going to give us 6 terms, and then we'd have to distribute a 3 in there. But we don't have to do all of that for this one. Really, we just have to look at what's the highest exponent going to be for each one of these terms and multiply those together, and we can get the highest exponent. So here, when we FOIL this out, when we do the x times the x, we're going to get an x squared term. Here, we just have a single x term. So x squared times x is x cubed, and there's no x on the outside. So x cubed, or 3, is going to be the degree of this polynomial because it's the highest exponent it's going to have. And the maximum number of turning points is that minus 1. So 3 minus 1 is 2 turning points. Now that's a maximum as well, so it does not have to actually have 2. All right. Some third-degree polynomials just look like a u, and they really only have 1. Okay, I'm sorry, not third-degree polynomials. Fourth-degree polynomials look like a u and only have 1 turning point there. All right, and the last thing it says is determine the end behavior. The end behavior. That is, find the power function that the graph of f resembles for large values of x. So if we were to multiply all of this out, we'd have a leading term. It would be something x cubed, right? We don't actually know what that number is yet, but we're going to find it pretty easily. And that's going to be the only term that really matters when x gets very large or very small, because the cubic function, or something being cubed, grows much faster than things being squared or things being just multiplied by x or even constants. So for small values of x, yeah, there's going to be a pretty big difference depending on which of those terms are. But for large values, when we're talking about 10 million or 10 billion, or negative 10 million or negative 10 billion, then it's going to resemble extremely close to just the first term in that polynomial. So really all we have to do is find that first term. And we kind of almost did earlier. So we know when we FOIL this out, we're going to get an x squared term. And we know we have an x term here. So x squared times x is x cubed. And then we just have to multiply it by this 3 on the outside. So our power function that's going to resemble large or small values of x is going to look like 3x cubed. So what's going to happen when we put large positive values into x? Well, cubing it is just going to give us an even larger positive real number, and multiplying by 3 is just going to give us even a larger one. So as x gets larger and larger, as the graph goes farther and farther to the right, the y values are getting much, much higher. Now let's look at to the left. So put in a really small value. Let's say negative 1 million. Well, if you take negative 1 million and you take it to the third power, a negative times a negative times a negative gives you a negative back. So this is going to be an extremely small negative number, or you can look at it as a very large magnitude negative number. So this is going to be much bigger than the trillions, right? Negative. So, and then we multiply that by 3, and that's still going to stay negative. So as our graph goes out to the left, as our x values get smaller and smaller and smaller, our y values are going down. They're getting smaller and smaller as well. All right, that's it for this one. If you have any questions, let me know, and have a great rest of your day. Thank you.